In this video, we'll be going over equilibrium and the effect of delta G non-standard, or the effect of changing the concentration during the reaction, okay, or before the reaction if you mess with the initial conditions. So if you disrupt equilibrium, which way will the reaction shift? And we're going to go over how those changing conditions can affect the equilibrium position. So first a couple of side notes about delta G and delta G standard. So remember that if delta G has a degree symbol, we're referring to delta G or free energy being measured under standard conditions. Okay, and standard conditions are 25 Celsius. The pressure is at 1 bar, which is about 1 atm. And also, all concentrations are 1 molar. So all the concentrations. So as we know, during a chemical reaction, these are constantly changing the amounts. Like let's say we have let's say we have the production of ammonia from nitrogen and hydrogen. Okay, so over time, like if you start off with 1 molar, of everything, or 1 atm, like over time these amounts are going to go down and this amount is going to go up. So right away they're not going to be 1 molar anymore. So this reaction will proceed until you reach a certain point. So and this is why what we can deduce from looking at delta G non-standard. Okay, so this is non-standard. If you ever see this in your textbook, the delta G without the degree symbol here, okay, with nothing there, then it's referring to delta G non-standard. All right, so we're to calculate delta G non-standard during a reaction, we use the following equation. So we use this: delta G non-standard equals delta G standard, whatever it was standard, plus RT times the natural log of Q. Okay, and so let's point out some terms here. So this right here is, of course, the free energy at a given point during a reaction, is how I like to think of that. This is calculated from one of the 4 ways we went over. So we get this. So this is not changing. That's an important note about this. This is not dynamic. It's not changing. It's just here's what the free energy is measured under standard conditions. So this number is not dynamic, it's static. It's just changing. It's not changing at all. It's just staying still. Whereas this number here is going to be changing during the course of the reactions. It's constantly changing because of the other term in here, because of this term right here. Okay, namely because of Q. So Q will be changing. Temperature can also change during the course of a reaction, like if it's producing heat and some of that heat is going back in towards the reaction. Okay, so but most importantly it's because of Q. The amounts are changing, as I was describing earlier, over time. Okay, so this we're going to use one of the 4 ways to get this. So use one of 4 ways to calculate it. So the most common way is to use delta GFs, okay, the free energies of formation. Okay, that's the most common way. Another way is, of course, to use the Gibbs free energy equation, is to use this. So you would need to know the enthalpy of formations and minus T delta S standard. Okay, and you would look up enthalpy data and entropy data, and then you could get delta G that way. Okay, you could also get it from using Hess's law. Uncommon, and in fact, I've never actually seen that asked uh, on an AP exam. Is they tend to not ask stuff about using Hess's law. So uncommon, but I will mention it in case you guys see it again in college. So the other way is to use delta G equals negative RT ln of K ln of K. Okay, so that's another way you can get it. But these are the most common is ways 1 and 2, and number 1 is the easiest. You could just look up GFs and get it that way. Okay, so on to the other. So mention a couple things about these other terms. R is, of course, it's not the gas constant. This is the energy constant since we're solving for energy. So this is the converted form of R for that incorporates joules. So here it's 8.314 joules per Kelvin times mole. And this number here is typically given in kilojoules per mole, because the common way to get it is from these values, which are usually in kilojoules per mole. So when I perform calculations using this equation, I usually just change this to kilojoules. So I usually just call it 8.314 times 10 to the negative third kilojoules per Kelvin times mole. And then T is whatever temperature the reaction might be occurring at, is T temperature. And of course, this has to be in Kelvin to match this term here. Now, the last thing is Q. So here's what makes this kind of like, is the whole point of this entire tutorial actually is Q, what Q is all about. So Q, if you remember, is basically the way you do it is you use the equilibrium expression but using initial amounts. Okay, so we want to use the initial concentrations, or of course we could use pressures here. If you use pressures, by the way, they have to be ATM. Okay, and concentrations, of course, is molarity. So this is done the same way. So it's going to be products initially, that's the 0 there, over reactants initially. Okay, and we're going to see that over the course of a reaction, we're going to be, actually let me write, or the partial pressure of the products over the partial pressure of the reactants. Okay, so as a result of that equation, let me write it again up here. So the G non-standard equation, we have G standard plus RT ln of Q. Then you get the following graph. So this is free energy, or G non-standard. And on the x-axis, we have the progress of the reaction. So you'll have like kind of like this U-shaped curve, looks something like this, where over here your reactants have a lot more free energy than your products. Okay, and just because the amount is too big, so your reactants are way more than your products. And also, so if we look at Q would end up being really small, okay, and highly negative. So your delta G, so this number, so if you take the natural log of fractions, you're going to get like these negative numbers. So imagine if this is really tiny and this is huge, your reactant amount, okay, then your let's pull up the calculator for a second. Okay, if we take the natural log of, let's say, some fraction, some really small number, like let's say 1 times 10 to the negative 10th. Okay, then we get these really big negative numbers. Okay, and that would ensure that this is less than 0 if that occurs. So delta G non-standard would be less than 0. Okay, and this reaction, and we know from Le Chatelier's principle that when Q is really small, Q is less than K. Okay, and we don't have enough product and we have way too much reactant. So we know when that happens that the reaction, this is from our previous unit on equilibrium, that our reaction, when this is small and this is big, the reactant amount, it needs to shift to the right from the reactant side to the product side to try to get back to K. So it needs to make this number big, okay, and then it needs to make this number small, and it does so by shifting to the right. So it shifts right when we have that situation. So I'm going to make this big arrow going like that, meaning it shifts to the right. So if you have this scenario, okay, over here, this is the other extreme. So this is if you have way too much product, okay, and it's way more than your reactant. Okay, if that's the case, then if we look at Q, we have product over reactant. Okay, then so this number will be way too big and this number is too small. So if that's the case, you have Q ends up being much greater than K. Or if it's, if you're right here, it's a little bit bigger than K. Okay, but if you're way over here on the extreme end, then Q is way bigger than K. So Q needs to become smaller. So Q, to get smaller, this needs to go down and this needs to go up over time. Okay, so to do that, it's going to shift from the product side back to the reactant side. So it will shift. And we know all this. This is really nothing new. This is all the same stuff from our equilibrium unit. So it's going to shift to the left to increase that reactant amount and lower that product amount. Okay, and we'll be taking the natural. So this is going to be some huge numbers. So let's pull up the calculator again. And let's just take the natural log. Let's just take the natural log of 1 times 10 to the 10th, like some huge number. Okay, and then we get, so we get some huge positive number in that case. Okay, so this RT ln of Q ends up being a big positive number. Okay, and that ensures that we're way over here, and it means that delta G non-standard, okay, delta G non-standard is going to be positive, is greater than 0. Okay, and so this will shift to the left. Okay, and right here in the middle is when, so right here in the middle, let's make a star right here in the middle. Not a star, let's just make a dot, big dot. Okay, so right here is when delta G non-standard is 0. Okay, where the free energy of the product equals the free energy of the reactant. Okay, and also what happens here is when Q, so Q will do its thing and try to get back to K. So if you're way up here, so if you're way up here, Q will Q needs to get smaller by shifting to the left. You're way up here, Q needs to get bigger, so it's going to shift to the right. Okay, and when Q finally equals K, you're at equilibrium and there's no net shift, so delta G non-standard equals 0 in that case, and Q also equals K. Also nothing new. This is all from the equilibrium chapter. So let's take a look at our equation here when we're in the middle dot right here. So if we set Q equal to K and delta G non-standard equals 0, we'll plug in 0 for that, and we get delta G standard plus the RT ln of, instead of Q, we're going to write K there since Q equals K. Okay, and now we're going to move this term over and solve for delta G. So it would actually equal the negative RT ln of K. So this is the connection between free energy under standard conditions and the equilibrium constant. Okay, so and we'll take a look at that in a minute, but I wanted to expand a little bit on this side of the curve and this side of the curve. Okay, and we're going to do that in the next tutorial.